So yeah, thanks a lot to the organizers. It's really a very nice event, and it's great to be here. So today I will tell you about, try to give you a flavor of where things are at in terms of probing non-equilibrium phenomena in correlated systems with quantum processors. So in particular, I will focus on the experiments we did using the Google quantum processor. And then in the second part of the talk, I will also switch to more, let's say, theoretical issues, and I'll give you an overview of some of the ideas we've been developing, essentially aiming to connect quantum many-body dynamics with open quantum systems, and this gives rise to interesting ideas for new classical simulation methods based on the concept of temporal entanglement. So as we know and could appreciate during the first days of this conference, classically simulating quantum many-body phenomena is a big challenge, and there is this wonderful idea of instead using processors, machines which operate quantum mechanically. So, and really there has been a lot of remarkable experimental progress, such that such quantum simulators, synthetic quantum systems now exist, and perhaps one of the first has been systems of ultra-cold atoms in optical lattices, right? And on the one hand, they have some of the aspects, they can realize simple models that we think about in condensed matter, and they offer very nice tunability, so you can change their dimensionality, control lattice, interactions, disorder within a pretty broad range. And so that's been one of uses of the systems. But of course, they're also very much unlike conventional materials, in particular in that they're hanging in vacuum, right, cooled and trapped by lasers, and so there is no, for example, there is no phonon bath, or there is no heat bath in the sense we're used to in the solid state systems. Moreover, many of the systems have pretty long time scales compared to what we see in the solid state, and therefore it is possible to monitor the revolution in real time, and that really opened a whole new field and made this quantum simulation platforms really sort of very nice for probing non-equilibrium phenomena in interacting quantum systems. Now, this difference compared to solid-state systems also shows up in terms of kinds of experiments you can do. So rather than measuring, so for example, measuring conductivity or heat capacity in the system that's typically challenging, but instead what is natural is quantum quench setup. So for example, you can think of a disordered optical lattice and then initializing atoms in some relatively simple state, like a product state where they're sitting on different, let's say here they're sitting on every other side. And then the system evolves under its own interactions, and then it's possible using tools of quantum optics to image this evolution with single site, in real time resolution. There are also other types of non-equilibrium phenomena you can access. So in particular, you can periodically modulate the parameters of your system, and that also gives rise to new Fourier phenomena. By now, there are really a few very different quantum simulation platforms, right? Each offering its own natural set of experiments, and for example, some of them have long-range interactions, some of them have short-range interactions. So apart from the cold atoms that I mentioned, right, another powerful platform is superconducting processors, right? So this is a simulator of a different kind because it's digital. So here rather than thinking about this regime where you have a physical system and you have good control over its Hamiltonian, right? Here, instead, you really think about quantum gates, right, and realizing a quantum circuit, right? So, in principle, these machines aim to be able to implement any many-body quantum operation. And there are also other very nice platforms such as Rydberg atom arrays and reptines. Now I will, so as I said, I will tell you about a couple of experiments done on the superconducting quantum processor. So let me just spend a couple of minutes reminding you how they work and what, where things are at the moment. So idea of superconducting qubits goes back to this notion of macroscopic quantum coherence, right, developed by Leggett and others a few decades ago. And here, your quantum mechanical variables. So let's say if you think about Kuiper pair box, so one or two superconducting islands connected by the Josephson junction, your quantum mechanical variables are the number of Kuiper pairs on this islands that go across junction and the phase difference, right? Phase difference, and this becomes essentially a nonlinear oscillator. So you have a bunch of quantized levels which are not exactly equally spaced because of nonlinearity, right? So this is illustrated here, and then you couple to the right. So the lowest two states become your computational state. So those are the qubit. This is your qubit, right? And of course, it took couple of decades of hard work from experimentalists to learn exactly what are the best parameters and how to control these devices efficiently. And so, and where things have gotten in the last few years is there are, right, so these qubits can be made into a processor with about, let's say, order of 50 to 100 so-called transbond qubits, right, where couplings between them, so they're arranged in this square geometry and coupled by tunable couplers, and essentially using electric field pulses, one can realize both single qubit operations. So here I'm using XYZ to denote Pauli operators for a qubit number J. So you can, for example, apply controlled rotation around x-axis, right? You can also apply gates acting on two qubits. So for example, this corresponds to turning on interactions, Ising interactions between qubits for some time, right? And then you can run, so on this machine, you can run quantum circuits. So here time goes this way, right? And for example, this is, right, these are entanglement gates, and then single boxes are single qubit operations. So this is the Sycamore quantum processor. And one, milestone experiment from now 4 years ago has been demonstration of sort of aiming to simulate a problem that is classically hard, right? And this goes under the name quantum supremacy. And really, in this experiment, the goal was to run a circuit which would create as entangled many-body state of your qubits as possible. So this was a random circuit, sort of leading to a very entangled but otherwise featureless state. And then the idea was to sample distributions of wave functions of this many-body, distribution of amplitudes of this many-body wave function. And so this is a problem that is challenging for classical computers. And so recently this has been also, right, this has been done with much improved hardware. Now, this was, of course, a very nice demonstration, right, that these machines are at least approaching regime where they can do things that are challenging for classical simulation, right? So, and from that point of view, from this point of view, actually, non-equilibrium dynamics provides a very natural class of problems. And this is because if I go back to quantum quench setup that we briefly discussed, and for example, I have an interacting spin system, and I prepare it in a simple product state, and then I let degrees of freedom interact, right? So what generally happens, these states, due to interactions, they become very entangled. So, for example, in a one-dimensional system, I start developing entanglement that grows linearly in time. And there is a remarkable link between entanglement and complexity. So things that are wave functions which are entangled are also hard to describe classically. And right, that, on the one hand, one challenge is to find problems which are already, which can be simulated on the modern day quantum processors, but also this constantly pushes us to think about new efficient classical methods out of equilibrium. So, and these are changing problems, so there aren't so many options. And so, and together, together, hopefully this leads to finding, for example, using this quantum processor for discovering new phenomena. Now, so let me just give you a 2-minute overview of the different regimes of quantum dynamics that people have been studying theoretically and experimentally over past decade or even more than decade. So, of course, so if I think about this quantum quench experiment, the most natural scenario that comes to mind is thermalization, right? That so I start, so my system is quantum mechanical, but it starts out in some equilibrium configuration, but then things, there is energy exchange, and then I bring, right, which brings me to a steady state that looks thermal, right, as we expect in statistical mechanics. And indeed, so many quantum mechanical systems behave that way. They're colloquially, you could say they're such that they can act as a good thermal bath for their subsystems, right? And way to understand the origin of thermalization is the state thermalization hypothesis, which tells you that actually in such thermalizing systems, even individual eigenstates have thermal observables and therefore are highly entangled, because in this case, entanglement entropy becomes thermodynamic entropy, and right, and so and therefore generally thermalization is associated with high entanglement. And of course, this idea of thermalization and associated scrambling of quantum information is being actively researched also in other contexts such as quantum gravity. Now, a very natural and fruitful question has been to look for mechanisms to avoid thermalization, right? This most natural possibility. And so, and here, right, so we said that there are systems which act as, which scramble quantum information and act as a good thermal bath. On the other end of the spectrum, we have many-body localized systems, right, where disorder via phenomenon of many-body localization essentially stops exchange of energy, right? Your system is localized and is actually a bad bath, so it's not capable of thermalizing subsystems. And underneath, so the origin of this in a way is the existence of many local conservation laws which are associated with localized states. Another quite a different mechanism to not completely prevent but drastically slow down thermalization is prethermalization. And typically, so here you find approximate integrals of motion, and so as we and others found out, there is a set of phenomena where actually this approximate integrals of motion would be exponentially long-lived in some parameters, and so and I will show you an experiment where this shows up. And this has quite a few applications in Floquet engineering, and also leads to stable edge modes in Floquet systems, which I will focus on next. There are other phenomena such as quantum many-body scars, but I will not focus on them today. Now, of course, one constant challenge in the in this experiment is fighting effects of environment. Right, on the one hand, you want to control your system, which means it couples to something, right, to the fields that you use to control it, but that also leads to unwanted environment effects. And so we have in particular, your system can decay, right, giving the energy into the environment. So that would bring your state into trivially, for example, into the down state of the qubit, zero state of the qubit. And you also have dephasing, so which means that your wave function starts acquiring phase that you don't control. And typically, right, once you add decay and dephasing in your system, so that brings your system, drives your system into a trivial state. And also from the point of view of computational complexity, actually that typically simplifies things. And therefore one challenge for for us is to understand whether there are types of experiments and types of many-body quantities we can reconstruct in these experiments despite decoherence. And so next, so let me jump to the experiment and give you one such example that we found. Right, so this was probing Majorana-like edge modes using the processor I just described. So, of course, as we all know, there is a notion of topological phases of matter, right? And one key property is the robust degeneracy of many-body ground states. This has given rise to this fascinating idea of topological quantum computation, where you use this robustness to encode qubit states into superposition of degenerate ground states. And one very nice system where this degeneracy arises is a one-dimensional p-wave superconductor, right, where essentially the two ground states are related by, there are zero energy Majorana modes at the edges. There is a complex fermion associated with two of them, and essentially, depending on whether it's filled or empty, you connect between the two ground states. There has been and there are ongoing efforts to see and control Majorana modes in the semiconducting nanowires, right? And there has been, so here, right, the way people look at them is tunneling into the edge and then hunting for a zero bias peak, which signals zero mode. Now, these experiments are quite challenging, right? Because it's difficult to control the nanowires and control disorder. So our aim was to study the Majorana-like edge modes in a very different system, which we understand much better, but where you encounter a different set of challenges. And here, right, so first of all, we don't have a Hamiltonian. Instead, we run a quantum circuit, and we are dealing with qubits and not fermions. And a model that maps onto Kitaev model of p-wave superconductor is a transverse field Ising model. And here we are realizing Floquet version of it. So it's discretized transverse field Ising model. So you apply X rotations and then Z rotations with two parameters. And this leads to first challenge, right? So here in this Floquet system, there is no ground state notion, and instead of eigenenergies, you are dealing with quasi-energies, right? And turns out that for this particular model, which is integrable, right, which maps onto free fermions as an original Kitaev model, so you still have Majorana edge modes described by this operator chi, right? And moreover, depending on the values of these parameters G and J, you can get either a zero Majorana mode or pi Majorana mode. And so, pi Majorana mode, instead of commuting with your evolution operator, it anti-commutes with it. And this leads to spectral pairing of a different kind. So it's not a degeneracy of levels, but actually levels are paired, so they differ by the quasi-energy pi. And so, and what you will see, right? What you will see is that the mechanism of robustness of this mode to, for example, adding noise and interactions is quite different from Majorana's nanowires. Of course, they're not, right? We are not talking about full topological protection, but it's a partial, so they're long-lived, right? That's what we are talking about. And the mechanism behind it is prethermalization that I mentioned. And so let me jump to the experiment. So first question that arose: how do we see these modes in the experiment? And okay, so we use Sycamore processor, cut a chain of some 45 qubits through it, right? And run this quantum circuit. In the spin language, the Majorana-like operators, you can think of them as a superposition of products, right? Products of Pauli operators. So, and then you get longer and longer Jordan-Wigner strings. So you can think of it as a quasi-local operator of this form. And the idea was to do the quantum quench experiment. So you initialize your system in a bit string state. So qubits 0, 1, 0, 1, 0, 1, right? Or spins up, down, up, down. And then you measure correlators of different operators. And what you expect is that correlators which enter the expansion for the Majorana operator, they would behave differently compared to the ones which don't. And so here is first set of data. So this is just the first, right, to see how ZZ correlators at the edges of the chain. So the y-axis is the qubit number. And then we see whether the system remembers where the spin or qubit was initialized. And so what you see in the bulk of the chain, right, there is a form of thermalization. So you forget where you started, but then at the edges, the behavior is very different. And you see these persistent oscillations going on for some 200, 300 Bloch cycles. Moreover, once you take the Fourier transform of this, so you can see that this gives you the quasi-particle spectrum. So and here is the result of how the quasi-particle levels evolve as you tune the parameters of your system. And you see, right, you see this bright peak. So that's exactly the pi Majorana mode. And then you see the splitting, right, as you go through the topological phase transition into the non-topological phase. Then you see the splitting, and you can study how the splitting depends on the finite size, and you, as expected, you find that it is exponential, right? It is exponential in the system size, right? So the larger is your chain, right? The smaller is the splitting because it's harder and harder for the two edge Majoranas to talk to each other. Now, right? So we wanted to go further and reconstruct actually the full wave function, if you wish, of this Majorana operator. Right, so here, of course, we started with the example where we know what to expect. So we know the form of this operator, and then so our naive expectation was that multi-qubit operators, right, multi-spin operators here would be much harder to access because each qubit experiences dephasing and decay, right? So naively you would expect, okay, those things would get washed out very quickly by noise. But turns out that reality is different. And actually, so here you see the temporal correlators of different operators. So they would correspond to essentially Majorana operator a few sites away from the edge. So that has a small overlap with the Majorana mode. And what you find is that, of course, the less local operators are smaller in the absolute value, but they decay with the same rate as the largest, right, as the operator Z1, which has the largest overlap with the Majorana. And this is actually, turns out this is the general fact that if you have an integral of motion under weak noise, that becomes a slow mode of your Lindbladian. And that allows for an accurate reconstruction of this operator. So, and here is the result. So for example, for some parameters, we could reconstruct the full Majorana operator up to 12 sites, right? So measuring 12 qubit observables and still getting precise signal. So, and this is one, I think, interesting surprise, right? Which has applications beyond this experiment. And so, and just to give you one more interesting piece of information here. So far I've been showing an integrable model where we know the answer, but now let's explore how this mode responds once we break symmetry and integrability. So let us now add random Z field and see how the response will change. And so what you see on the left is that this pi Majorana mode is quite robust. So you see the oscillations, right? Oscillations at half the frequency, half the period as in the time crystal, right? And moreover, it's pretty insensitive to disorder. While if you take an edge modes of a different kind in the full KXY model, there is a sort of non-topological edge state, then you see that it is actually very sensitive to disorder. Okay, so I think I'm at about 27 minutes, right? So we started at 5 past. And I should aim to be 40 plus 5 for questions, right? 35 plus 5, okay, it's 40 minutes, okay. Okay, so then maybe, so since I have about 8 minutes, right? So let me just flash the second experiment, recent experiment that we did. So here's the idea, just tell you the idea, and then of course I'm happy to discuss or ask me more during the questions. So here's the idea was a little bit to move away from this setup of quantum quenches and really thinking about isolated quantum many-body dynamics, as you also saw in the Majorana experiment, right? And in those experiments, you always think about noise as your enemy, and you try to either reduce it or find tricks to decode what your system is doing. But here we wanted to instead engineer dissipation and turn it into a friend, right? And here, of course, this idea is known of using engineered dissipation has been known in the field for many years, right? And it was proposed, so it's known that with dissipation you can do quantum computation, and for certain classes of Hamiltonians, so-called frustration-free Hamiltonians, this is a good tool for many-body state preparation, at least in theory. But our goal was really to go and push it beyond frustration-free Hamiltonians and take a physical system and engineer, right? Use some of the qubits as a bus, right? And engineer a type of dissipative evolution that would drive your many-body system to a interesting steady state. And so, we have a theory which essentially is based on trying to remove quasi-particles from your system in the most efficient way. And so let me just to give you some flavor of this in 1 minute. So we, in particular, studied this very system with these quasi-particles and came up with protocols where you can essentially, so what you see here is the steady state distribution of the quasi-particle numbers, and blue means cold, right? There are no excitations, and then yellow means there are some excitations. So you see that you can cool the system pretty nicely using dissipation, and then moreover, you can purify the states, and for example, you can drive the system to a state where you can extract quantum critical correlations. And we hope that this will become a more scalable and more sort of another way to prepare sometimes correlated states that we don't know in advance. So you can also do it in 2 dimensions. But now let me spend the remaining 5 minutes to give you switch a bit to theory, right, and talk about this connection between quantum many-body dynamics and open quantum systems. So, and here, typically, right, a lot of methods we have, tensor network methods, they're based on the notion of spatial entanglement, right? They work when your spatial entanglement is not very large, right? Ideally, it is, area law or maybe logarithmic in the system size. So then methods like methods based on tensor networks are very powerful. But we wanted to change this. And of course, non-equilibrium phenomena are still quite challenging for tensor networks. So we wanted to change the philosophy a little bit and say, well, often what we want is the local observables, right? So let us actually focus on the time trajectories of these local observables and then treat the rest of my many-body system as a bath, as an environment. And that's technology for formulating it goes back to Feynman and Vernon. So essentially, you can integrate out the bath and end up with an influence functional, right, which is a functional on the space of your system's trajectories, which encodes, memory and non-Markovianity of your bath. And so what we found that with this approach, you can get quite a few nice insights. You can get some exact solutions, and even more interestingly, you can find new efficient methods based on low temporal entanglement, right? So now instead of thinking about spatial entanglement, we think about this object and we think about its entanglement depending on the evolution time. So now the goal becomes, if we find the temporal entanglement is low, then we can compress this using tensor networks. And this overall gives you a different perspective on many-body dynamics. And here is, just an illustration. So for example, if I take once again the model that we already saw in the Majorana experiment, Floquet model, so you find that typically, this model is chaotic, so it's thermalizing, there is a lot of spatial entanglement, but turns out that the influence functional, so here I'm just plotting the tensor network describing discrete time evolution. Turns out that for some model parameters, this influence functional is extremely simple. It's a product state on your temporal space of trajectories. Once you add noise, this gets even more efficient because the memory time of your bath is reduced, and that's actually something we used, right? This algorithm we used to model noisy circuits showing up in the Majorana experiment you just saw. Now, more on the theory side, so where you can prove something about the scaling of temporal entanglement are integrable models. So actually, for any quadratic fermionic bath, we can think of this functional influence matrix as a wave function, quadratic wave function in the temporal domain, and we can show that temporal entanglement obeys area law. So here you see an illustration for, once again, this model without the Z field. This extends further. So actually it turns out that for systems with quasi-particles, temporal entanglement generally shows favorable scaling because, if you have quasi-particles, they don't come back. So you only interact with them once and they don't carry this memory back to you. So here is an example from an integrable XXZ spin chain where scaling is logarithmic. And that, of course, that tells you that these systems are actually amenable to efficient tensor network methods. So we've developed some applications to this problems of dynamics in interacting many-body systems. But in retrospect, the most natural application was actually, it was to the quantum impurity models, and which already have been discussed in a couple of talks so far, which show up. So quantum impurity model where your reservoirs are have a non-interacting bath, maybe with some non-trivial spectral density, and then all the interactions are on the impurity. And of course, this shows up. This is a classic setup in the transport and mesoscopics, and they play play an important role in embedding methods for modeling correlated materials such as DMFT. And so, and our approach here was to essentially, so you can easily write down the influence functional for non-interacting reservoirs. And since we understand temporal entanglement, we know that this can be efficiently represented as a matrix product state. And there is a constructive algorithm by Fishman and White to do that. So then we can convert this Gaussian state into a matrix product state, and then all we need to do is to contract it with the evolution of the impurity. And just to flash before I take questions, so here's benchmarking it on a standard setup, which is a quench. So this is real-time dynamics, so quench in an Anderson impurity model. And as I said, temporal entanglement scaling is favorable. So even when your reservoir is at 0 temperature, temporal entanglement scales only logarithmically in time. And indeed, so you find, once you implement it, you find that this works pretty well. So, and you can describe dynamics of different states. So here you see probabilities, initialized impurity in the spin up state. You see how it decays slowly, and then there is a rise of the spin down probability. So that describes the slow dynamics. It's generally challenging, and it describes the formation of the Kondo singlet. And so, and this is right. So this right away gives you state-of-the-art performance for this real-time problems. And so just 1 minute before I stop. So, and recently, we've also tried to take it to the core of DMFT and try to see how it does in the imaginary time as an impurity solver, right? So this was a very nice collaboration with Benedict, Antoine, and others at Flatiron group. And okay, so here, object you're dealing with is not an influence functional, of course, but rather retarded action. So we called it retarded action MPS algorithm, RAMPS. And so, and here is what the scaling of errors looks like for versus bond dimension of your MPS and versus temperature. Key message: it is polynomial, and it seems like we can get to relatively low temperatures. Of course, here quantum Monte Carlo is essentially exact, so we are benchmarking against it. But here our hope is that this approach does not have a sign problem, so maybe with further improvements we can try to attack some multi-orbital models. And with that, so let me conclude. I try to give you, I know it's a pretty broad crowd, so I try to give you a flavor of where things are in terms of probing, right? So, and argue that quantum processors and simulators are at the stage that they can give surprises and useful insights into our understanding of non-equilibrium quantum matter. So I mentioned the set of mechanisms for essentially avoiding thermalization, right? Highlighted new phenomena that arise out of equilibrium, such as noise-resilient edge modes. And so, and towards the end, mentioned this notion of temporal entanglement, right, which seems to give a useful connection between many-body dynamics and open system dynamics. And with that, so let me stop and thank my collaborators on different projects. So Julian, Alessio, and Michael in Geneva have really pushed the influence functional story, and Shao from the Google team has been leading the experiments, right? And then so Vadim, Pedram, and all of Google Quantum team, and then so Benedict, Antoine, and others at Flatiron, right, on the imaginary time description of impurity models, and Lorenzo and collaborators with whom we also worked on temporal entanglement. So thanks a lot.